Hello maths fans! Dr. Tom Crawford here at the University of Oxford, and today we're looking at Fourier series. In the last video in the Oxford Calculus series, we saw how to find a solution to the heat equation, one of the first partial differential equations that you will study as an undergraduate mathematician. And we saw that this solution was valid provided we could express our initial heat profile as an infinite series of sine and cosine terms. This is exactly what Fourier series allow us to do. Fourier series work by taking advantage of two key properties of sine and cosine. The first is their periodicity. So if I have a function sine of x or cosine of x, then both of these are going to be 2 pi periodic. Now, we want to consider a more general periodic function defined by f of x. So let's suppose that our function f is 2L periodic. So we have a function f of x which is going to be 2L periodic. So this means it repeats every 2L as you move along the x-axis, much like sine and cos repeat every 2 pi. Now, because we want to construct our function f using an infinite series of sine and cos, we actually want to consider a certain form of sine and cos, which are going to be 2L periodic also. So in fact, what we're going to look at here is rather than just sine of nx or cos of nx for some integer and then we sum them, what we're going to do instead is to consider sine of n pi x divided by L and cosine of n pi x divided by L. Because for each value of n, and again we're going to add together all of these as n increases from 0 to infinity. For each value of n, these functions are now 2L periodic. And so they match with our function f, which is a general periodic function. The second property that we need to construct our Fourier series is going to be the orthogonality of both cos and sine. And I'm going to show you an example to demonstrate exactly what we mean by the word orthogonality. So suppose I want to do the following integral. I'm going to integrate from minus L to L. You'll notice this has length 2L, which is going to be the period of our function. And I want to integrate sine of, let's suppose we have m pi x divided by L. So that function, again, is 2L periodic, multiplied by sine of n pi x divided by L. And we're integrating with respect to x. Using the appropriate product to sum formula, this tells us that the integral becomes minus L to L. There's going to be a factor of a half, which I'm going to put outside of the integral. And then inside we have, I believe, a cos of m minus n pi x over L. And then we subtract cos of the sum, m plus n pi x over L. If you're unfamiliar with the product to sum formulas, if you start from the second line here and use the standard trigonometric addition formulas, you will see that the various terms you get cancel out and you're left with exactly what we have at the top. So this is now an integral that we can do. This is the advantage of turning the product into a sum. We have two pieces, we can integrate cos of something and use the reverse chain rule to get the answer. So we can do that and say this is a half times the integrated part. So that's going to be a sine of m minus n pi x over L. That's not changed. And then we've also reverse chain rule given us an L divided by pi times m minus n on the bottom there. And then we subtract off, and again we're going to get an L over an m plus n times pi. And that's also come from a sine m plus n times pi x over L. And it's between minus L and L. Okay, so I think that's correct so far. Now, there are two things that can happen here. And this is a very important technique or thing to always check whenever you're doing any maths problem, not just this one. This could be 0. At this point, there's nothing telling us that m and n are different. We know they're both positive integers because remember, we're interested in adding together this infinite sum from n equals 0 to infinity of all of these different sine and cosine terms. So we can certainly assume that they're positive. Without loss of generality, let's say m's bigger than n. But they could be equal. That's the key thing. So we're going to split this up into two cases. So we've got one case when m is not equal to n, which is the one that I've written out here. So provided m is not equal to n, I am not dividing by 0, and therefore I can evaluate this expression. So when I do that, I could, of course, explicitly substitute in the L terms and add together those 4 pieces, but you can spot what's going to happen. Because when I substitute in L, this becomes pi L over L. So the L's cancel, and I'm left with a sine function of an integer multiple of pi. It's sine of some integer times pi. If you think about the graph of sine, it is 0 at every integer multiple of pi. So this will be 0 when x is L. Similarly, this is sine of an integer multiple of pi L over L gives me 1 again. So this is another sine of an integer multiple of pi, so that's also 0. Minus L, the exact same thing is going to happen. We substitute in here, we get sine of negative integer times pi, still 0, minus sine of negative integer times pi, it's still 0. So all 4 individual terms, plugging in 2 from each limit, they're all 0. So provided this is valid in the first place, provided this is valid, the answer here is just 0. So we get 0. Now, the interesting case is exactly when m does equal n. So for this one, I'm going to take a different coloured chalk so we can see this more clearly. So when m is equal to n, we go back to this stage here and say m is now equal to n. So what does this mean? Well, this, m equal to n, that gives me 0 now. So this is cos of 0. Doesn't matter what's here. This is cos of 0, so we know that becomes a 1. So this now becomes 1. And then here, m and n are again, they're the same thing. So we've got a 1 minus cos, and what we're going to get inside that bracket will be 2n pi x over L. Okay, so proceeding from here and integrating. Again, we're going to get the factor of a half outside. The term in 1, that integrates to give me an x. Then the cos term, again, comes from the sine term. So that's now minus, this thing's still valid. So I will get L over 2n pi, and then we're left with sine of 2n pi x over L, and that's p minus L and L. Plugging in the limits just as before, we're going to get to half of x, which is L, so we get there, writing it down here, we get a half, and then I'm going to get an L, minus L over 2n pi times sine of 2n pi. L over L is 1. It's an even integer multiple of pi. Still 0 again. So nothing from that. And then we get minus, bracket, when we plug in x equals minus L. So it's minus L. And again, when we plug in minus L, that gives us a minus 1 in here. We get minus an even integer multiple of sine. It's also 0. So it's minus L, brackets. So factoring all of those things out, we get L. So what we've seen is when we have a product of two sine terms, and we will do the same for cos in just a moment, when we have a product of two sines with an m and an n, we've seen that if they are different values, they are integer values, but if they are different, we've seen that the answer is 0. And if they're equal, then we actually get exactly L. So what we can do, or a nice shorthand notation that we can use, is to say that this integral is equal to L, which was the answer we got when they were equal, multiplied by the delta function. So I'm going to write this as delta m n, and this is where delta m n takes the value 1 when m equals n and 0 otherwise. So it's just a shorthand way of expressing exactly what we found here in terms of the integers having to be equal in order to get a non-zero answer. Now we can do the exact same thing with cosine. So we consider the integral from minus L to L of cos m pi x over L, which remember is a 2L periodic function, multiplied by cos of n pi x over L dx. As before, we want to use the appropriate product to sum formula to turn our product of causes into a sum. We can then integrate those terms individually, and again, as before, we're going to get a different answer depending on whether m is equal to n or not. Following through all of those steps, and I really do recommend trying this one for yourself, you'll actually get the exact same answer. So this is equal to L, half of the length of the period of our function, multiplied by, again, delta mn. Now that just leaves a final combination, which is going to be the integral from minus L to L of sine of m pi x over L times cos of n pi x over L. So for the first two, we had two sine terms, two cos terms, so the only other possibility that could happen when dealing with cos and sine is that we have a sine multiplying a cos. Now for this one, we could proceed and use the product to sum formulae, just like we've done for the first two. However, we can be slightly cleverer and actually spot something about the function that we're integrating. So we know both of these are 2L periodic, and importantly, we're integrating over a symmetric region. We're integrating from minus L to L, so we're integrating over a region which is symmetric about 0. Now sine is what we call an odd function. So label that as odd. And to see why, or to see what I mean by this, let's look at its graph. So if I have sine function over here, then I'm going to have something like this, and then it's kind of reflected over here. So we say that sine, or it's true that sine of x is equal to minus sine of minus x. And that's how we define an odd function. So it's odd. I like to think of it as almost like being flipped in the line y equals x. Now cos is even. Cos is an even function. And what that means, if I draw the graph of cos, is we start at the top, we go down, and then we come back up and then down, and then we go up and then down. I like that. So cos is reflected in the y-axis. So we know that cos of x is the same as cos of minus x. And that defines an even function. So because we have an odd function multiplying an even function, together we have overall an odd function. And this works in just the same way as it would with odd and even numbers. Or if you want, you can follow through these definitions and convince yourself that when you multiply a cos and a sine, it does satisfy the property of being an odd function. So this whole thing is odd. So whilst we could try and work out its shape, but of course that will vary for different m and n, the fact that it's odd tells us that we have this sort of reflective symmetry in the line y equals x or y equals minus x. So what that's going to mean here is whatever we have on one side of 0, we're going to have like the exact negative on the other side. So when we do the integral, and this is true in fact for any odd function, if you integrate any odd function over an interval which is symmetric about 0, you will always get 0. So we can use this property to immediately conclude that this is in fact going to give us 0. So in summary, we have a total of 3 orthogonality relations which are going to be incredibly important when deriving our Fourier series. The first one tells us that two sine terms, when multiplied together and integrated, we get 0 unless they have the same integer m and n. For cos, we see that again we get 0 unless they are the same cos term. And if we have a sine and a cos, because that's an odd function, that will always integrate to give us 0. And these three relations are actually going to be key in deriving the coefficients for our infinite series of cos and sine terms. Now, some of you may have noticed that these orthogonality relations that we've just derived are stated for integrals from minus L to L. Now, we definitely need an interval of length 2L because our functions are 2L periodic, and that's clearly an important relationship between the function and the interval over which we're integrating. But a perfectly valid question might be to ask, do we always get the same results here over any interval of length 2L? If you wish to investigate this further, then I recommend checking out the Maple Learn worksheet linked in the video description below this box, which takes you through a step-by-step proof of this property. I've also included some exercises looking at the properties of odd and even functions, as well as some further exploration of the orthogonality relations that we've just derived. And if you get stuck with any of the questions, then don't forget the Maple Calculator app is here to help. Just download the app onto your phone, take a photograph of the equation you want to solve, and then click the steps feature to see a breakdown of the solution. Now that we have the orthogonality relations, let's put them to use in deriving our Fourier series. So we begin with a general function, f of x, which is 2L periodic, where of course L can be any number. And what we want to do is rewrite f of x as an infinite series, an infinite sum of cos and sine terms. So let's suppose that is possible. Let's just go with it and see what happens. So assuming we can do this, we can rewrite f of x is equal to the sum from n equals 0 to infinity of the unknown coefficients an times cos of n pi x over L plus the unknown coefficients bn times sine of n pi x over L. And the idea is that adding together all of these terms is going to give us f, but of course we need to determine what these coefficients are. Just saying this exists doesn't really help us when we're trying to solve a problem. We need a method of determining the coefficients an and bn. Now if we focus on n equals 0 first, so when n is equal to 0, and this is the only one we're going to do, I'm not going to go through all different values, but there's something special about n equals 0. So when n equals 0, we're going to get a0 times cos of 0 plus b0 times sine of 0. Now, sine of 0, well, that's just 0. And cos of 0, well, that's just 1. So all we're left with here is actually going to be this first coefficient a0. So this is a much simplified case when n is specifically 0. And so what we tend to do in our definition of the general Fourier series is, in fact, to start the sum from 1, and then we add in what we call the 0 coefficient, which is often labelled as a half times a0. The choice of the half there will become apparent shortly, but for now you can see this is a constant because when n is 0, we're going to get a constant term. So the question now becomes, how do we calculate our three different coefficients? We want a formula for a0, the constant term, a formula for an, and a formula for bn. And the trick here, which really all of the theory of Fourier series relies on, is going to be to use our orthogonality relations. So to begin with, coefficient 1. Let's take this equation, which remember we've assumed exists. This Fourier series, we're saying, suppose it exists, let's see how we might calculate the coefficients. So let's take this whole equation and let's integrate both sides of the equation from minus L to L. So we can say minus L to L times f of x dx is equal to the integral from minus L to L of a half a0 dx plus the sum. And here what I'm going to do is take the integral inside the sum. I will talk more about that. Well, I will talk more about why that's allowed at the end of the video. But for now, let's just go with it. I'm going to take the integration inside the sum and say this is then the integral from minus L to L of an cos n pi x over L dx. And then we've got another infinite sum, integral minus L to L of bn sine n pi x over L dx. Now what do we get when we do these integrals? Well, this one's relatively straightforward. This is just a constant. So when you integrate a constant, this just gives me a0 x over 2 between L and minus L. So that will be a0 L over 2 minus a0 L over 2. So I'm just going to get two lots of it. So it's going to be a0 L. So this first integral here gives me a naught multiplied by L. Now this one, we have a constant, an, multiplied by cos n pi x over L. Now if I integrate cos, so that will give me a n, and then I've got to remember to do L over n pi, and then I'm going to get sine of n pi x over L between minus L and L. Now when I substitute in these values for x, so I get sine of n pi, well that's 0. And then I get sine of minus n pi, well that's also 0. So this whole thing is 0, in fact. And similarly, when you integrate over here, you integrate your sine, it gives you some multiple of cos, and cos at these 2 points, they're going to actually perfectly cancel out. Precisely because each of these functions, for any value of n, each of them is actually 2L periodic. And we're integrating over period, total length 2L. So this also gives you 0. And again, if you want to do the integral and substitute in, you can see that explicitly for yourself. So both of these vanish, and even though there's an infinite number of them, each individual piece is always 0, because the fact that these integrals were 0 is entirely independent of the value of n. So all of these pieces are 0. So all we're left with is the integral of f is exactly a naught times L. So we can just rearrange that equation. So putting this all together, we can just say, well, therefore, 1 over L, dividing both sides, times the integral from minus L to L of fx dx, that is exactly a naught. So the first of my coefficients that I want to work out in this Fourier series is just simply given by integrating my function f between minus L and L, and then putting a 1 over L outside. That is why we had the half, because it simplifies to this nice neat formula at the end. So we have the first of our coefficients, a 0, given by integrating f, but how do we work out an and bn for a more general value of n? The trick lies in the integration and the application of the orthogonality relations over here. So you'll note we didn't actually need these relations to get this first result, but what we're going to do to get an and bn is actually going to be to combine this idea of integration on both sides of the expression along with these orthogonality relations that we've derived. So to get our second coefficient, we're going to take the an in general. What we want to do now is to integrate both sides of the equation, but we want to first multiply by cos of m pi x over L. So the left-hand side is fx cos m pi x over L dx. That's just multiplying the left by cos m pi x over L, and then integrating. So now we have to do this for everything on the right-hand side. So this is now equal to a half a naught, so I can take that out the bracket, a half a naught, the integral from minus L to L of cos m pi x over L dx. Again, we're going to assume that it's okay to interchange the infinite sum and the integral. I'll talk about that at the end. So that then gives us a second term, which will be the sum from n equals 1 to infinity. Then we've now got the integral from minus L to L of an cos n pi x over L times cos m pi x over L dx. And then we've got the sine term. So plus the sum from n equals 1 to infinity, the integral from minus L to L, bn sine n pi x over L times cos of m pi x over L dx. So hopefully you can immediately see these two look like our orthogonality relations. And that is what we're going to use to figure out what these coefficients an need to be. So the first integral, we have something very similar to what we just saw in step 1 for our a0 coefficient. We're integrating cos, which is 2L periodic, between minus L and L. It's going to be 0. So this is 0, since 2L periodic function. Now over here, let's look at this second term, because we've got a sine of n times a cos of m. That's exactly what we've got here in our third orthogonality relation, and we saw here that this was 0 no matter what value of m or n. So remember here, m is a general number from 1 potentially through to infinity, and n covers all possible values from 1 to infinity. So this covers all possible pairings of sines and coses. But by the orthogonality relation, we know this is always 0. So this whole thing here is 0 by orthogonality. Orthogonality. Precisely from this third one up there. So that just leaves this term. Now we've got a cos n pi x over L times a cos of m pi x over L. And that's exactly what we've got over here. It's L times delta m n. So what we can do is say this here becomes, we've still got the an because that can come outside. So we're left with the sum from n equals 1 to infinity, and then doing the integral, but taking out the an because it's constant. We've got an L delta mn. Now, L is just a constant, so we can just divide by that. That's no big deal. But the n here, an, depends on the sum, but it's being multiplied by delta mn. Now remember, the delta function was 1 when m equals n. When they are the same value, it gives you 1, and it gives you 0 when they are different. So what this does is it actually picks out exactly when m and n are the same thing. So even though there are an infinite number of terms in this sum, this ensures that we get a single term, and that single term is when n and m are the same thing. So whatever value of m I pick, if I pick m is 1, m is 2, m is 3, every time I pick a value of m, this will pick out exactly that coefficient. So we can actually say this whole thing is just L times a m. Because again, we only get a non-zero answer to this integral when n and m are the same thing. So what this means for our coefficient in our Fourier series, neatening this all up, is we're actually left with this expression here. So we've got the integral from minus L to L of fx times cos, remember we fixed this, cos of m pi x over L dx. That's the left-hand side of our expression. And all we've got on the right was we've got 0 from this, L, am. That's it. So this whole thing, we can actually just say, well, if I just put am here, then this is 1 over L times all of this. So again, you think about it by saying, if I want to know the coefficient am, so say I want to know a2, the way to get a2 is to take my function f, multiply by cos 2 pi x over L, integrate from minus L to L, all of these terms disappear, and I get a2. So we can do this for any value of m, So this gives us a way to calculate now every single coefficient that goes up here in our Fourier series. Finally, to get the term Bn, which is the coefficient, the constant coefficient of our sine term in the infinite Fourier series, we follow the same approach. And as I'm sure most of you may have realized, we're going to now multiply by sine of m pi x over L and then integrate. So for our third coefficient, we do exactly that. As we've seen a few times before now, this integrates to give me 0 since it's 2L periodic and we're integrating over an interval of length 2L. This term is a cos times a sine. That's 0 always by orthogonality. So this is 0 by orthogonality. And then finally, we have this expression involving the two sine terms. Exactly as we just saw with the cos terms, we're going to get this result here. This is equal to L delta mn. And then we've of course got the sum from n equals 1 to infinity of Bn. The delta function picks out exactly the Bm coefficient and absolutely nothing else. So this whole thing together is L times Bm. So again, we can rearrange and get our final formula. Bn is equal to 1 over L, the integral from minus L to L of fx times sine n pi x over L dx. So we have our formula here for all three coefficients. This allows us to determine the constant one, a0. We integrate f between minus L and L. For our constant in front of the cos term, we multiply by cos n pi x over L, multiply f by that, and then integrate. And for our coefficient here on the sine term, multiply f by sine and integrate. So this gives us explicit formulae for all of the coefficients, which means we can indeed write down our Fourier series for any 2L periodic function f. The best way to get to grips with Fourier series is of course to play around with them for yourself, which is exactly what you can do in the accompanying MapleLearn worksheet. There is a question which takes you through a full derivation of the Fourier coefficients for the sawtooth function and allows you to see how the series provides a better and better approximation to the graph as you include more terms. As always, the worksheet is linked below and is available for free courtesy of MapleLearn. Now, I did mention that I would briefly address the issue of interchanging the sum and integration sign, as of course our derivation of the formulae for the Fourier coefficients in all three cases did rely on this interchangeability being okay. I'm not going to go into the full details because that would require a course in analysis and I don't want to go off on that much of a tangent. But the key aspect or the key property that we need of our sum for this to be justified is that the sum is uniformly convergent. Now what this means in a nutshell is that not only does our sum converge to a limit, which of course has to be finite, it has to converge to something. Here it's clearly converging to f. So not only does it have to converge, but if you were to give me an epsilon, any epsilon, small number that you can think of, my task is to find an n sufficiently far down the sum that I can always add up terms to that value of n and be within epsilon of the final limit. So that just means that the sum converges. Now, if it's going to be uniformly convergent, then for any epsilon that you give me, I actually need to find an n which does not depend on x. So whatever n I pick in order to get within epsilon of the limit, that n has to be true or has to hold true for whatever value of x is selected based on the domain upon which this series converges. So for normal convergence, I can pick an n which depends on x, so I can pick a different value of n depending on the values of x we're interested in. For uniform convergence, my n, the distance I have to go down the sum, it actually has to hold true no matter what value of x we pick. So provided uniform convergence holds, we're able to interchange the integral and the sum, and therefore our derivation of the coefficients is totally sound. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all soon. Take care.